I want to begin by asking the question, why are we here? And I don't mean what is the purpose of life? What I mean is, why are we here at the Feature Store Summit? And Laura kind of made this point for me earlier. The reason we're, of course, is because feature engineering is an expensive process. And feature stores can help you with that, because once you've handcrafted your features, you could place them in the feature store and then retrieve them for later use. So feature stores can help you reduce the cost of feature engineering. But I want to go a step back and ask, well, why is it that feature engineering is expensive? And the reason it is expensive is because this is how you spend 90% of your time. Imagine you're a data scientist, and I imagine for most of you that shouldn't be too hard. So let's just say you're a data scientist, and you're probably an expert on machine learning, an expert in statistics, but you may not be an expert on the thing that you're trying to predict. For instance, if you wanted to do a credit default prediction, you might say, well, I don't understand anything about banking. Well, how do you do that? Well, what you would then do is go to an expert, somebody who really understands the thing you're trying to predict. And together with that person, you'd come up with a set of hypotheses. And you would then take these hypotheses and implement them in the form of features, usually in SQL or pandas or whatever. And then you would evaluate these features, and you would go back to the domain expert with the results of your evaluation, and you would find, well, some of these features have worked very well, but some of these features did not work as well as expected. And then you would have to discuss, well, why didn't they work? Is it maybe because you used the wrong data? Is it maybe because you haven't implemented this correctly? Or is it maybe because the domain expert was wrong? And this cycle would go on for a couple of rounds, and then in the end, you could go ahead and deploy your model. But the point is that all of this takes a lot of time. And what we can learn from this is feature engineering is expensive, not because you need special equipment, not because of the computational costs involved, that is negligible. It is because expensive people, data scientists, domain experts, have to spend a lot of time and manual labor engineering these kind of features. So the next obvious question is, well, wouldn't we be able to automate this somehow? And if you think about this, it really doesn't make sense that we're not doing this already. For instance, take image data. We can do automated feature engineering for image data. Well, this is what a convolutional neural network is there for. And we can also, as Laura mentioned in a talk earlier, we can also do this for text data. And by the way, we can also do this for speech data, speech recognition. So we can do this for forms of data that computer scientists refer to as unstructured data. But when it comes to relational data, structured data, well, we still do it by hand. So let's summarize. We can do it for unstructured data. We can't do it for structured data. And frankly, that just doesn't make sense. So the purpose of this talk is I want to introduce you to approaches, algorithms, techniques that can be used to close that gap, how we can automate feature engineering on relational structured data and time series as well. And I want to start with just the simplest approach, the easiest approach you could possibly think of. And by the way, simple is good. And that is a propositionalization approach. I sometimes also refer to this as feature engineering by brute force. And the simplest, most commonly used propositionalization algorithm out there goes something like this. You have a bunch of aggregations, you have a bunch of columns to aggregate, and then you combine them all. So you take the average of column one, the sum of column one, the min of column one, the max of column one, the average of column two, the min of column two, the max of column two, the sum of column two, and so on and so forth. I think you very much get the idea. Well, let's talk from a practical point of view about the pros and cons of propositionalization, of the propositionalization approach. Well, the first thing is these are very simple interpretable features that look very, very similar to manual features. And that's a big plus. I mean, just in the discussion earlier, we talked about the importance of interpretability. So propositionalization very much fits that bill. It's also very easy to implement propositionalization algorithms. In fact, you don't really have to do this yourself because there's so many implementations out there. There's feature tools, there's TS-Fresh, H2O's got something like this. There's a company from Ireland called Expanse Analytics. And then, of course, there's us, getML. So all of these tools that I've mentioned, they have implementations of the propositionalization approach in one form or another. On the con side, we've got the problem of feature explosion. I'll discuss that in greater detail in just a minute. And then it's very hard to implement efficiently, and that is also something I will discuss soon. The next thing is, because these are very, very simple features, well, it doesn't capture complex relationships. And finally, because it's not really a supervised approach, we're going to generate a lot of garbage features. So in the end, you probably have to do a feature selection. Now, on the earlier slide, I said that propositionalization is easy to implement, but it's hard to implement efficiently. And now I want to sort of back this up a bit and sort of resolve this apparent contradiction. So what I've done here is I've taken our own tool and I've benchmarked this on 5 different data sets against popular implementations of the propositionalization algorithm. So it's really the upper part here that I'm concerned with, which is the runtime. And of course, when it comes to runtime, lower is better. And now both of these tools that I've used for reference, feature tools, TS-Fresh, they're very popular open source tools. Both of them are written in Python, and both of them can be deployed on either Pandas or Dask. So they both piggyback these existing data frame libraries. And when we benchmark our implementation against that, what we find is that we're about 35 to 179 times faster than these kind of implementations on Pandas or Dask. Now, why is that? The main reason this is happening is because they have to do a lot of redundant operations. They have to calculate the same thing over and over and over again. By contrast, what we did is we designed our own database engine from scratch in C++. And this database engine is really, really optimized for the task of automated feature engineering on relational data. And that has enabled us to really, really reduce redundancies, both in terms of computation, but also in terms of memory. Another thing you would find is that they actually consume a lot more memory than they have to. And this is what I'm saying. It's actually very easy to write something like this in Pandas or top of Apache Spark maybe, but if you really want to get something very, very efficient, we have to put in a lot more effort. And that is why I'm saying, well, it's easy to implement, but it's hard to implement efficiently. Right. So the next algorithm I want to introduce to you is kind of similar to propositionalization. At least the features look kind of similar, but it sort of already has a bit more of a machine learning feel to it. And this is what in the academic literature is called MRDTL, or multi-relational decision tree learning. And the features kind of look like this. So again, you've got an aggregation, you've got some sort of column that you aggregate, but then you add these kind of conditions. You can do that in propositionalization as well, but because you would very, very quickly have a lot of features, it's very, very limited what you could do there in the propositionalization approach. But with MRDTL, you can build slightly more complex features. And the reason that is because MRDTL uses a supervised decision tree-like algorithm. So basically, it roughly works like this. You start with some sort of aggregation, you start with some sort of column you want to aggregate, and then you add different conditions. And then, and this is where the main difference to the propositionalization approach comes in, you've got some sort of loss function. And for each of these conditions that you try, you see, well, does my loss function improve, yes or no? And then, of course, you keep the condition where you've got the most reduction in the loss function, if any, and you keep that is now part of your feature, and then you start adding more condition until some sort of stopping criterion is met. So if you're familiar with decision tree learning, this would seem all seem very familiar to you. And then, of course, once you're done with the first feature, you move on to the next feature. And from a theoretical perspective, I think this is very, very interesting, because what we can do here is we can piggyback, we can make use of all of the research on decision trees, on decision tree ensembles that has been done before. So to say it with Isaac Newton, we can stand on the shoulders of giants. We can use established, proven paradigms like bagging and boosting and gradient boosting and so on and so forth that are widely used in traditional machine learning, and we can easily apply this to the problem of relational learning and automated feature engineering. So this is what, from a theoretical perspective, I really, really like about this decision tree approach. So now, from a practical perspective, I would like to discuss the pros and cons. So on the pro side is this captures more complex relationships than the propositionalization approach, while at the same time the features are still reasonably close to manual features. So you might sort of get away with, thinking that these are actually manual features, and you can interpret them. On the con side, you've got the problem of feature explosion, and I promise it's going to be the next slide. And then, of course, efficient implementation. This is actually a much bigger topic than it is for propositionalization. The idea for the algorithm first came out in the late 90s, and it's not really that hard to come up with the algorithm, to be quite honest with you. But then for 10 years, there were papers, there was academic research, and well, how can we make this more efficient? How can we implement this efficiently? How can we really, really minimize redundancies? And having written this myself, having done this myself, having implemented this myself, I know just how difficult this is to really, really get rid of all the redundancies and redundant operations that you would have in there. And then, of course, you have a problem that you generally always have with decision tree learning, is that information might be lost due to the greediness of the algorithm, the greediness of the approach. Okay, I'm going to keep my promises, and now I'm going to talk about feature explosion, because I really think it is a very, very important and very, very underestimated problem. And I want to analyze this on a semi-theoretical level. Think about how we're writing features with MRDTL or maybe by hand. And I want to do this in the most generic way possible. So what we usually do when we write relational features, it's some kind of aggregation over some kind of column. And then usually on top of that, we apply some kind of condition based on some kind of other column. As you can see, I'm trying to be as generic as I possibly can here. And as you can see, let's think about what we have when we have 10 columns. So when we have 10 columns, there are 10 columns we can aggregate, and there are 10 columns we can use for our condition. So in total, that adds up to 100 possible combinations. And if we have 100 columns, well, same thing there. There are 100 columns we can aggregate, 100 columns we can use for the conditions. So in total, that is 10,000 possible combinations that we have there. So the feature space grows quadratically with the number of columns. And the very important thing to understand is that this also affects manual feature engineering. It's not just about automated feature engineering. This is also a problem with manual feature engineering. I've known people who've been writing features manually for the better part of a decade who are not really aware of this problem. But when you implement automated feature engineering algorithms, you realize just how big of a problem it is. It is a very, very underestimated problem. And I realized that we needed to come up with a solution for this. And our idea basically is not to write your features like this. Instead, write them as you can see them on the screen here, like this. So the idea here is you've got some kind of aggregation, but what you aggregate actually isn't a column. What you aggregate are learnable weights. And then all of your columns can only be used for conditions. They cannot be used to be aggregated. And the beauty about this solution is that now the feature space grows linearly with the number of columns and not quadratically, which is obviously much better than MRDTL. And we would expect this to work much better on data sets with many columns. And again, the algorithm is very, very decision tree-like. Now you pick an aggregation function, you add different conditions. For each of these conditions, you calculate the weights. Well, you figure out whether the loss function improves, and until some kind of stopping criterion is met, after which you move on to the next feature. And as the name implies, what we do here is we actually make use of the gradient boosting approach, to ensemble learning, which we sort of piggyback for this idea of relational learning. From a practical point of view, I want to discuss the pros and cons. On the pro side, obviously, you've got the fact that there is no feature explosion. You can build any number of features. It builds on state-of-the-art machine learning paradigms. I mean, gradient boosting is one of the most widely used machine learning paradigms out there. On the con side, the problem is that it does not allow for more complex aggregations. It's really, really hard to learn your weights through something like count distinct or median. And at the same time, it's also harder to interpret. I'll show you in just a minute. And this is just speaking from experience here. But I've done a lot of projects with FastProp. I've done a lot of projects with RailBoost. And my general experience is that when you have a data set where the predictive power really stems from 1, 2, 3 columns, and most of the other columns are more or less irrelevant, then propositionalization approaches will actually work a lot better than RailBoost. But when you've got more complex data set where the information is more spread out over many, many columns, well, that's where RailBoost really shines. And from the theoretical perspective that I sort of discussed earlier, this is very much what you would expect. So the experience that I have, very much matches the theory. Okay, now what I want to do is I want to move on and sort of give you an impression what relational learning can actually look like in practice. And I'll quickly explain the example dataset for you. So the example dataset is a public domain dataset. It's about a fictitious company called Works. And what this fictitious company does is they sell bicycles. And we thought it would be very, very fun to help this fictitious company manage customer loyalty, predict the customer loyalty. And what we've got here, this data set very much by design is supposed to resemble a standard customer, enterprise level customer database. So you've got your order header, you've got your order details, you've got product information, you've got special offers, you've got stores and order reasons, and all of these sort of things. Okay, so now I want to leave the presentation and move on to the notebook. And as you can see, I haven't started this, but I'm going to run it now. And while I'm running it, I will explain to you what is actually going on here. So the first thing we want to do is we want to get the data set, of course. This is retrieved from what is called the relational dataset repository. And if you're in any way familiar with relational learning, you probably would have come across the relational dataset repository. It is very, very cool and very, very helpful. And the next thing that you want to do is you want to assign roles to your data. So you would have to tell the tool what you want to do with it. I always say, well, the idea of roles is roles versus types. Is types describes what a column is, but roles describe what you want to do with it. And because the thing cannot know what you want to do with it, you have to tell it. By the way, this is something that is not unique to our tool. If you use other tools like feature tools or expands analytics, it's very, very similar. You would have to assign roles to these columns. Okay, so we don't only do this for one table, we do this for a whole set of tables. And the next thing, of course, we want to do is we have to define our target variable. What is churn? What is customer loyalty in the context of bicycles? And the definition that we use here is, well, if somebody made a repurchase within 180 days, well, that person is a loyal customer. And if they didn't, they're not a loyal customer. Now, of course, for the data that is less than 180 days away from the end of our data set, we cannot use that because we cannot know 100% for sure whether somebody is a loyal customer or not. So we're going to discard that data and not use it for our analysis. And yes, one thing you want to do, of course, is to split your data set into a test and training set. You usually would only have to do that on the main table that also contains your targets. You wouldn't have to split any of the other tables. So yeah, in this case, we're just going to randomly use 80% for training and 20% for testing. Okay, and then there's one more thing that you have to do. And again, this is very, very typical across the board for all of the automated relational learning tools that I'm aware of, is you would have to feed the model with the abstract data model. So you would start with your main table, and then you say, well, I want this table joined over this ID with this table joined over there, this ID, and then onto that table, I want that. I think you get the idea. So you basically want to provide a basic skeleton of your relational data set that the algorithms can then traverse. Okay, right. So the next thing I've done is that I've set up two pipelines. So the first pipeline is based on a propositionalization approach, and the second pipeline is based on RailBoost. So both of these are approaches that we have discussed. And it appears that I've been talking for a very long time, because now the first algorithm has already run through, and the second algorithm has also run through. So both of them has run through. So now what I can do is we can now look at the features that have been learned while I was talking. So the pipeline that we see here is that is the propositionalization approach that I've used. And the one thing that you would notice, these are the feature importances. And the one thing that you've noticed is that really, of the many features that we have generated, only a handful of them, only small percentage of them are actually useful. And this comes back to what I said earlier. This is very typical. You get a lot of garbage features that are not really useful for your prediction. So in this case, what I probably should have done is a feature selection. I would have done this if this were a real world thing, but of course I wanted to demonstrate this problem of the garbage features. So yeah, let's take a look at some of the most important features that we have here. So as you can see, this very much looks like something you would engineer by hand. This is not in any way out of order. These features you might reasonably think are manually engineered features. Let's take a look at the other pipeline. If we actually compare these two pipelines, we see that RailBoost does a bit better than the propositionalization approach. And if we dig a bit deeper, what we find is that the predictive power is sort of spread out over the columns. It's more than just 2 or 3. So it's not that much more. So you would expect RailBoost to do a bit better, but not that much, which is exactly what we observe. And of course, I want to show you what a RailBoost feature trained by this algorithm might look like. And as you can see, well, it's a bit more complicated. So I think you couldn't possibly think that this has been written by a human, and then you'd have a harder time interpreting this. But of course, particularly for more complicated data sets, you get considerably more predictive power. Okay, so there's one more thing that I haven't really talked about yet in my talk, but it's a very important problem that has been discussed by many other speakers, which is the problem of feature drift. The idea that features sort of lose value over time, and then you have to sort of manually re-engineer them. And I think this is one of the major advantages of automated feature engineering, that you don't have that problem. If you think that you've got feature drift, all you have to do is retrain your pipeline, rerun the script, and then you've got new features that are adapted to the new data. So not only does automated feature engineering make it easier to build a working prototype and then bring that working prototype into production, it also makes it a lot easier to maintain your model in the long run. And if you're a software developer, you know just how important that is. Okay, so I would like to conclude my talk by saying this. If you want to reproduce any of the benchmarks that we've done here, if you want to, if you don't believe anything, if you don't believe some of the things that I've said, or you're just interested and want to dig a bit deeper, what we've actually done is we have set up a GitHub repository. It's called getML demo, that contains all of the benchmarks, all of the notebooks that I have in here. So everything that I've shown you is based on public domain data. We completely show all of the work that we do, and you're absolutely invited to reproduce all of the claims that I have made in this talk and all of the notebooks that I've run. And actually, there's much more than I've discussed. So you're very much invited to try to reproduce all of this. Thank you very much for your attention. I'll now take your questions.